Hello everyone, I'm Leonardo Guevara, first author of the work titled Road Planning for Multiple Entrailers in Manual Harvesting Operations. For the past few years, mobile robotics and automation technologies have been successfully integrated into agricultural processes. Most of the advances have focused on optimizing seeding, spraying, monitoring, or grain harvesting operations, as shown in the left picture. However, in specialty crop harvesting, the robots have not successfully replaced yet the judgment, dexterity, and speed of experienced pickers. In this context, rather than fully automating the harvesting task and thus replacing hand picking, it's more worth to automate crop transportation in order to create a semi-automatic harvesting system that takes advantage of both human dexterity and automated efficiency. In general, the manual harvesting process can be split into two main tasks: picking and placing the fruit into containers, and collecting the filled containers and transporting them to a collection station. According to the fragility of the crop to be harvested, the capacity of the container use change. When the container size change, the machinery required to transport them also change. In case of requiring a lot of payload capacity, a common solution is to use a tractor-trailer system, which consists of a standard compact tractor towing a chain of passive trailer with a beam per trailer, as shown in the figure marked in red. These kind of systems are also called end-trailers. When we are talking about autonomous navigation of this kind of trailers, we have to solve typical problems related to low-level tasks, which include perception, localization, and low-level motion control. But also we have to solve specific problems related to the motion planning of end-trailers, which include the maneuver planning for turning scenarios. As is illustrated in these pictures, maneuver planning is important to reduce the collision risk during transition between contiguous tracks. Now, when more than one vehicle is intended to use, other problems related to high-level route planning and multiple coordinations appears. In the literature, the cooperative navigation problem of the vehicle fleet has been focused mostly on operations where there is not interactions with human workers and where the vehicle storage of payload capacity is not considered as a relevant parameter. But in harvesting operations, despite the end trailers having a scalable payload capacity, it is still finite. Therefore, the vehicle has to interrupt the operation very often for unloading the filled bins at a collection station and then resume the harvesting by towing empty bins. Moreover, in manual picking operations, the picker performance causes the harvesting rate to change in dynamic and non-deterministic ways. Thus, road planning requires redefine the initial plan online as new non-inputs as revealed during the execution of the roads. In this context, this paper proposed for first time a high-level navigation strategy to manage and supervise a fleet of robotic and trailer vehicles during manual harvesting operations. The proposed strategy is summarized in this scheme and considers a combination of global planning that produces initial routes using a priori knowledge of the workspace, but also local planning that recalculates routes according to new information available about the changes in the workspace and harvesting rate. Apart from the road planning, the proposed cooperative navigation strategy is complemented with a field division into harvesting areas, an optimal temporary deposit location, and a harvesting sequence generator which optimizes the use of the machinery by selecting the proper number of trailers to use. According to this scheme, every time an active vehicle finishes a run and returns to the temporary deposit to unload the fruit, it becomes a backup vehicle. Then, the supervisory control computed by a central computer is continuously computing the backup vehicle departure time that must summarize the closest harvesting area to be interrupted. When a backup vehicle departure is required, the central computer selects the vehicle which tractor has been waiting the longest at the temporary deposit and has the highest payload at that moment. Now, according to this example, the backup vehicle's departure time is estimated based on the calculation of the time it takes for the active vehicles to reach the points where all the bins are filled, indicated as magenta stars, minus the time it will take for the backup vehicles to reach that point from the temporary deposit, indicated as black star. This example also illustrates the grid-based representation of the field used by the proposal to generate harvesting sequences and route plans. Then, each grid point has an integer coordinates x and y, being x the index number of each track and y an indicator of the kind of grid, which can be -1 or 1 in the case of headlands or 0 in the case of tracks with crop. If each point denoted by s is considered as an state, then the set of states is given by the equation 1. By using the a priori information about the expected amount of route per track denoted by m, and the coordinates of the grid points in a 2D Euclidean world, we propose to optimize the temporary deposit location by solving the optimization problem in equation 2, where the factor m was included to make the temporary deposit tends to be located closer to the area with more yield. As indicated in the illustrative example, each active vehicle can have different number of trailers, since it depends on the needs of the current sequence. Thus, it is not always necessary to use as many trailers as the tractor is able to handle. To find the suitable n, the harvesting sequence generator is iteratively computing harvesting sequences using different values of n, in a range within the maximum number of field trailers that the tractor can handle. The final solution of this iterative process is the one that among the setup solution with different n's allows generating a road that maximizes the number of tractors to be covered in a single run, but also minimize the distance to return to the temporary deposit to unload the fruits. In this way, the number of trailers used in each run can be different each time. The harvesting sequence generated during the iterative process must match with the picker's motion direction and machinery turning constraints. Thus, following the methodology presented in previous works of the authors, to reduce the risk of collision during headland turning, the end-trail capability to make transitions is constrained by the equation 3, where TC is called the end-trailer transition constraints, which represent the ability of the trailer to make transitions between two consecutive tracks. The grid maps in the right represent what the central computer knows about the environment before generating the sequences presented in the example on the left side. During this process, the main way, headlands, and non-completely harvested tracks are considered as free regions to move, which are represented as white grids in this example. On the other hand, tracks that do not belong to the assigned area and tracks completely covered are considered as restricted regions, which are represented by gray grids. That's the reason in the example A, B, and C, the tracks in the area 1 are all gray, because this grid map is focused on the area 3. And in the case of the example D, the only allowed grids are the tracks 4 and 5, which belongs to the area 2. The example in the grid map A also shows a special case where the transition from track 9 to 8 is not allowed for a 3-trailer vehicle. Then, to reduce a collision risk during headland turning, track 8 was painted in gray and it was restricted during this run. Once the harvesting sequence is determined, a vehicle route planning algorithm is implemented to generate optimal routes that connect the temporary deposit location with the initial or final point of the current harvesting sequence. Route planning can be computed by both the central computer using global information and by the onboard computer of each tractor using local information. The route planning using global information generates the initial route that the backup vehicle at the temporary deposit follows to reach the starting point of the harvesting sequence planned for that run. Examples of this route planning are shown in grid maps B, C, and D. On the other hand, the grid map in A shows an example of the route planning based on local information, where the starting point is the last point of the planned harvesting sequence and the goal is the temporary deposit. The route planning is based on the well-known A-star algorithm, which aims to determine a sequence of states which represents the shortest road from the initial point to the given goal. The A-star algorithm evaluates each possible element of the state space by combining the cost of moving from the current state to a possible successor, denoted by the cost Fs, and the cost to get from the possible successor to the goal, denoted by Fg. In this work, the cost Fs has been modified from the traditional version to minimize not only the distance traveled, but also the soil compaction, product of traveling on a track more than once. To this aim, the evaluation of possible successor is done by computing the total cost function in equation 5, when superindex k and k plus 1 denote the current state and the possible successor, respectively. LSG are the coordinates of the goal in a 2D Euclidean world, and R represent the number of times that a successor has been traversed before. As shown in the 4 grid maps, the headlands, the main way, and the tracks already covered can be considered as possible successors, colored in white color. while the tracks that do not belong to the area assigned to the vehicle and the tracks that have not yet been harvested are considered as obstacles colored in gray. It's important to highlight that when two vehicles are within their communication range, their local information can be exchanged and generate a grid map with fewer restrictions, as is shown in the example A, where the vehicle assigned to Area 1 received local information from the vehicle in Area 2, and that's why the track 4 is considered as possible successor although it belongs to another area. In order to evaluate the performance of the proposed strategies, a simulator of semi-automatic harvesting operation was implemented in MATLAB. The simulator has been developed to be able to recreate and evaluate different scenarios, which include the control of the machinery availability, field length, yield density, harvesting rate, and communication restrictions. As is shown in this video, for each iteration, the simulator shows the evolution of the tractor positions indicated in color circles following their road plans indicated in color lines. The field color of the circles and the tractors change between gray or green according to the harvesting state of the track or the entry load state. The pickers are not shown in the visual output, but their stochastic behavior was included by using a random variable with normal distribution to generate a dynamic harvesting rate. The vehicles moves according to this harvesting rate. Since it's a work in progress, it can be shown only preliminary results. The snapshot in the left side shows the evolution of the harvesting operations after 50 minutes of being implemented the proposed route planning strategy by comparing two cases. The upper grid map represents the results when 4 vehicles were available to be used as backup, while the other grid map represents the results when just 1 vehicle was available. According to these results, the first case produced fewer restrictions and thus the pickers are able to cover more tracks in the same time window than when the machinery availability was constraining to use a single backup for all the active vehicles. Then, in order to evaluate the machinery management when using the proposed harvesting strategies, a statistical analysis was carried out using a fleet of 5 end trailers but varying the tractor payload capacity. For these experiments, the maximum number of trailers admitted by the tractors denoted by Nmax was varied from 1 to 5. A statistical analysis was done in 4 different fields. Each one was executed 100 times, considering a random variation of 10% in the expected yield per track. The 3D bars diagrams indicates the average of trailers towed by the tractors in percentage. In the case when Nmax was equal to 1, the 100% of the runs were completed using n equal to 1, since it was the only choice. However, for the cases when Nmax was greater than 1, there are more options to choose from. According to the results, the n not always was the same that Nmax, which were probably because vehicles with n less than Nmax have a lower transition constraint. But even though in some circumstances it is useful to use vehicles with fewer transition constraints, it's more valuable to have a greater payload capacity when using n trailers. Summarizing, this paper described the use of multiple robotic end trailers vehicles to support the pickers during the manual harvesting operations. A high-level route planning strategy is proposed to coordinate the vehicle's departure times and generate routes that optimize the use of the machinery available while minimizes the total distance traveled, the total non-productive time, and the soil compaction. Since it is a work in progress, it was shown only preliminary results that are planned to be complete in the future work with extensive tests that evaluate the performance of the proposed strategy in different scenarios using that simulator. Finally, although the strategy assumes the use of robotic vehicles as a short-term alternative, it could be implemented with manned vehicles, where the harvesting sequence, departure times, number of trailers, and vehicles routes computed can be used as guidelines by the human operators and pickers. That was the presentation of this paper. Thanks for your attention.